Hi, this is Brandon Lewis with Embedded Computing Design here at the 2015 Sensors Expo in Long Beach, California. I'm here with John Austin, Product Marketing Manager of the Analog and Interface Products Division at Microchip Technology. And you're debuting a new product here at the show today, or actually yesterday, John. Can you tell us a little bit about it?
Yeah, the PAC 1921, which is a current sensing amplifier that has both a I2C interface to get data and configure the part, take advantage of a lot of features, as well as an analog output that is configurable to get the voltage, the current, and the calculated power off the bus.
Excellent. So why is the integration of analog and digital within the same component so important today for embedded developers?
Yeah, so the I2C interface, I mean, it allows a lot of flexibility. So I can, as a semiconductor supplier, I can integrate a lot of useful features that can help designers with their design, add flexibility to their application. And then by allowing the analog output, it reduces the data latency. So for applications that want to get the current and the voltage and the power out quicker, they'll read that off of the analog output. Sure. So from a production standpoint, it's better to use the analog, or a lot of customers prefer to use the analog output rather than reading it to eliminate the data latency.
Okay. Can you speak a little bit more to the configurability of the analog output within the PAC 1921?
Yeah, I mean, you can basically configure. That's the one thing that's very unique about this part, is that you can configure it for what data you want. I can configure it to get the bus current, the bus voltage, or the actual calculated power through the analog output. I can also configure the part, the output, to be useful for various types of systems. So in a lot of applications, there's multiple power supplies or power rails or systems. So I may have a microcontroller running at 3 volts and FPGA at 1.5 volts, where I have ADCs on those bus voltages, and I can scale the output of the analog output to accommodate those various subsystems. So that's a unique feature for the analog output.
Great. Do we have a chance to take a look at a demo?
We do. We do. We have a 1921 demo. So this is the PAC 1921 demo board. The first thing that you should note is all the ICs on the demo are actually from Microchip and manufactured by Microchip. So this would be the PAC 1921. Down here we have the MCP 2221, which does the USB to I2C to communicate between the PC and the PAC 1921. And then we have a couple of MOSFETs that generate a current source, a programmable current source that we can use to drive a current across the shunt. So just a really quick overview of the demo. The quickest way to get it running is actually just to hit function F2, and that will open up basically this calculation tab. And it puts it in a free running mode so that it's always converting data and displaying it in this tab. So this gives you basically the bus voltage, the current, and the power, and it also shows you the information in the accumulation registers. So down in the bottom left corner, you can see where you can adjust the voltage across the shunt. So you can do that either via this knob, I can turn it, or I can just type in a value. So I'm just going to put in 40 millivolts. And then up here are the tabs that actually show the data logs. So if I click on, say, the V bus, you can see that the bus voltage is at about right under 5¼ volts. And the sense voltage, you can see where I made the change, sitting right at 40 millivolts. And again, so if I change, I can tune this to different values, and the current sources change the current to generate that value across the sense resistor. And then here this shows the power calculations. So the other features that we discussed during the presentation would be the ability to change the resolution for the current and the voltage. So you can select those up here. You can select different current gains and voltage gains. So again, current gain up to 128 and voltage gain up to 32. And then this would be to enable or disable the internal digital filters. And that's pretty much it at a high level. So one of the most unique things about the PAC 1921 demo, and what I think is one of the most useful things, is when they designed it, they made it very modular. So I can connect here to an external I2C, my system to the I2C bus, bypassing the USB to I2C converter that's communicating from the PC and communicate directly to the PAC 1921. That way I can actually implement it in my system to evaluate it. And I can connect an external load through these connectors so that I can emulate either my system load or even connect my actual system load to the PAC 1921. And then I can bias everything up through this connector so that they all are on the same ground plane and it's at the same ground as the system I want to evaluate it in.
All right, great. Thanks, John. Where can we find out more information on the PAC 1921?
www.microchip.com/PAC1921.
Thanks again. This is Brandon Lewis with Embedded Computing Design. If you need to find more coverage on the show, check out www.embedded-computing.com or follow us on Twitter @embedded_comp. Thanks.